In chapter 14, we talked about conjugated systems. We talked about dienes, polyenes, dienes, a number of different things. In this chapter, we're going to talk about a different kind of conjugated system, a sort of special case conjugated system that happens in benzene and other aromatic compounds like benzene. So we want to look more closely at benzene and these other aromatic compounds. Let's get started. So we're going to start by looking at the simplest aromatic hydrocarbon, and that is benzene. Benzene has 6 carbons and 6 hydrogens, so 1 hydrogen on each of the 6 carbons, has a planar structure. All the angles come out to 120 degrees, and we typically represent it as a hexagon with 3 double bonds, 3 alternating double bonds. And that is our best structure of benzene that we can draw. Because of the 3 double bonds in the ring, we'll find that benzene has 4 degrees of unsaturation. Now, we're going to do a little bit later, we're going to do some calculations of degree of unsaturation. If you don't remember it, go back and look at chapter 10. And at the beginning of chapter 10, I show how to calculate degrees of unsaturation. Now, compounds, other unsaturated compounds like alkenes, alkynes, polyenes, all right, they will all undergo electrophilic addition reactions like this. So, for example, ethylene, if we react that with bromine, Br2, we will get 1,2-dibromoethane. If we take benzene and put bromine in with it, we get no reaction. Well, if we put bromine by itself, we get no reaction. We definitely don't get electrophilic substitute or electrophilic addition. So we will find that it is possible to react benzene with bromine, but only if we have a special catalyst called FeBr3 or iron 3 bromide. It's a Lewis acid, and instead of giving us an addition product, it gives us a substitution. As you can see here, we've replaced one of the hydrogens on benzene with a bromine. So that is a substitution. In the next chapter, we're going to talk about the details of this reaction, which is called an electrophilic aromatic substitution reaction. We'll get into all the details in chapter 16. But for now, we will say that benzene does not undergo normal electrophilic addition, and that is where we add an electrophile across a carbon-carbon double bond. We just don't get that to happen. So we want to look at the structure of benzene. We want to understand why benzene has the particular structure that it has and why we represent it in the way that we do. It all goes back to a chemist named Auguste Kekulé, who proposed that benzene was actually 2 compounds that were identical, but they equilibrated back and forth, where each one contained 3 carbon-carbon double bonds and 3 carbon-carbon single bonds. So we had the alternating pi bonds. In this description, the bond between any 2 carbon atoms, sometimes it's going to be a single bond, and sometimes it's going to be a double bond. And so his idea is that it went back and forth between these. This looks a lot like what we do when we do resonance structures. We draw 2 resonance structures that look like this, but he said it was 2 compounds. Now, keep in mind, he didn't have resonance structures. Resonance structures are a relatively new invention. They're a 20th century invention. So he didn't have the ability to think of it that way. So this was insightful, but it's not quite right. Benzene, we still draw it like this. And in fact, if we, instead of putting the double arrows, if we put a double-headed arrow, then it's the correct representation of the 2 resonance structures. But there's not an equilibrium. As with all resonance structures that we draw, it's not that it's going back and forth between the 2. In reality, it's a combination of the 2. So we don't have 2 different kinds of benzene molecules. We have one benzene molecule that's best represented by these 2 structures. So let's look more closely at the structure of benzene. If we're going to have a good structure, then that structure needs to account for these facts. One, it's a 6-membered ring and has 3 additional degrees of unsaturation. Kekulé structure definitely did that. 2, it's planar. Kekulé structure did that as well. 3, all carbon-carbon bonds have to be equal in length. This is where Kekulé structures didn't really work. Right? Kekulé structures, they definitely satisfied the first 2, but because it has 3 alternating pi bonds, that would imply that we would have 3 bonds that are shorter, the double bonds, and 3 bonds that are longer, and that it would be alternating back and forth where the double bonds would switch position. Again, our modern view of benzene is that it doesn't do that. All 6 carbon-carbon bonds in benzene are identical. And so that happens because of resonance, not because of an equilibrium process. So let's look at the resonance structures of benzene. So there are 2 equivalent resonance structures. We've seen these before. We can easily get from one structure to another just by moving the electrons using our curved arrow notation, moving those electrons so that we get the other structure. And note that here we are using the resonance arrow, not the equilibrium arrow. So that's a key difference. The true structure of benzene isn't the one on the left or the one on the right. It's this hybrid over here that is this. The true structure of benzene doesn't have a full double bond between any of the carbon-carbon bonds. It has one and a partial bond between each of the carbons. So the true structure is the resonance hybrid. The dashed line represent partial bonds. When we are doing mechanisms, we are going to draw the Lewis structures. We're going to draw these structures of benzene, these skeletal type structures. One, because hybrid structures are not legitimate Lewis structures. Hybrid structures are very important because they tell us what the molecule actually looks like, but hybrid structures don't tell us, they don't help us to account for the electrons. This very clearly shows that we have 6 electrons that are in p orbitals here, that are in the pi bonds. With this, it's a little uncertain as to how many electrons are there. So we like to use the Lewis structures when we're doing when we're talking about benzene, when we're talking about its properties, and when we're doing mechanisms on the reaction. In some textbooks, you will see an image that looks like this, and this is a variation of the hybrid structure. It represents that all carbon-carbon bonds have equal length, but again, it has the same problem that the hybrid structure has in that it's not a legitimate Lewis structure, and it doesn't tell us how many electrons are actually in the pi bonds. So you won't see me draw this usually, and you won't see it in the textbook very often. Except in talking about sort of generalized systems. So it's a quick way to draw it, but it's not an accurate way to draw it. Most of the time, we're going to use the Lewis structures. So one thing we want to look at is the length of the carbon-carbon bonds in benzene. As I mentioned, all of the carbon-carbon bonds are the same length. And so they come out to about 1.39 angstroms, and that's in between the length of a carbon-carbon sigma bond that you would have like in ethane at 1.53 angstroms, or a carbon-carbon double bond that you would have in ethylene at about 1.34 angstroms. The carbon-carbon bond length in benzene, 1.39, so it's somewhere in between. That tells you, and since they're all the same, that tells you that none of these carbons are true double bonds, and none of them are true single bonds. They are partial bonds. But they are definitely more than one bond. It's just not a full double bond. We will find that each carbon is sp2 hybridized, It's trigonal planar. That makes sense because there's 3 things that are connected to it, so trigonal planar. And all of the bond angles are exactly 120 degrees. So has this planar structure, 120 degrees. sp2 hybridized, which means that the sigma bonds between the carbons are represented by the overlap of an sp2 orbital on each carbon. The bond between carbon and hydrogen is represented by the overlap of an sp2 orbital with a 1s orbital on hydrogen. All right. The pi bonds are caused by the overlap of these p orbitals, which are perpendicular to the plane of the molecule. As I mentioned, the molecule is perfectly planar. All 12 atoms are coplanar, and the p orbitals are perpendicular to that plane. So we want to look at number 2 on the in-class assignment. So we're going to switch over to the in-class assignment. Okay. And we want to look at each of these bonds. So what orbitals are used to form the labeled bonds? We have bond 1, 2, 3, 4, and 5. All right. For bond 1, so I'll just put a 1 there. We've got a carbon. That carbon is sp2 hybridized. So we'll say a carbon sp2 hydrogen 1s. Because the hydrogen has just the 1 orbital, it's 1s. It's not hybridized. And then that is a sigma bond. Anytime you've got a carbon that's bonded to another carbon, and we're talking about the sigma bond, it's always going to be the hybrid orbitals of the carbon. For hydrogen, as I mentioned, there are no hybrid orbitals for hydrogen, so it's just going to be 1s. For bond 2, we've got a single bond between carbon and carbon. So one of the carbons is sp2 hybridized. That's the carbon that's on the benzene ring. And the other carbon is sp3 hybridized. And that is this carbon here. And again, that is a sigma bond. For bond 3, we've actually got 2 bonds. It's a double bond. So we'll do the sigma bond first. We've got a carbon sp2, and that is our sigma bond. And then our other bond, I'll do 3 continued here. Our other bond is a carbon 2p overlapping with another carbon 2p, and that is our pi bond. So there are 2 bonds there, and that's why we have to represent 2 bonds in that list. Bond number 4 is a single bond, so we just need to represent the 1. Each of those carbons are sp2 hybridized, so we've got a carbon sp2, carbon sp2, and it's a sigma bond. And that's all there is on bond 4. Bond 5, we're going to represent it as a double bond. So that carbon, on that one, we've got both of the carbons are sp2 hybridized. So bond 5, carbon sp2, carbon sp2, and that's our sigma bond. And there's also a pi bond in between those 2 carbons. So we'll put carbon 2p, and that's our pi bond. So there's 2 bonds with bond 5. Now, the other part of this question, of the indicated carbon-carbon bonds, which is the shortest? All right, so between carbon 2, 3, 4, and 5, which one is going to be the shortest? Well, the one that is a true carbon-carbon double bond will be the shortest. All right, so carbon 3 will be the shortest. Our bond 3 is our shortest. Now, we could go through and determine which ones do we think are the longest. Our longest should be the sigma bond that's sp2, sp3. This other one that's sp2, sp2, it would be pretty close, but probably a little bit shorter than bond number 2. But our definitely shortest bond should be bond number 3 between that carbon-carbon. It's an isolated carbon-carbon double bond. So it's got 100% double bond character on it. No resonance structures. So, okay. So now let's go back and look at the presentation. If we look at the electron density in benzene, we get something that's kind of interesting. Because we have overlap of all 6 p orbitals, they overlap above and below the plane, we get a continuous pi system that is both above and below the plane on the benzene. And then if we look at the electron density, we'll find that most of the electron density, or at least the higher electron density, is on the top and on the bottom of the molecule, with relatively low electron density at the hydrogens. That means that technically there is a partial positive charge on these hydrogens and a partial negative charge on the carbons. Now, it is a small charge, but it is there. It is there. Now, I'm going to show you a molecular model, one that I 3D printed. So I'm going to go back to this image. So this is a molecular model that I made for my classes. I designed it and 3D printed it. The carbons and the hydrogens, all 6 of them, are coplanar, so they're all in a plane. Between each of the carbons, the blue bonds here are the overlap of an sp2 orbital on carbon and an sp2 orbital on the adjacent carbon. So that is represented by that overlap, sp2 and sp2. The carbon hydrogens are represented by the overlap of an sp2 orbital on the carbon and a 1s orbital on the hydrogen. And so that is the overlap there. The p orbitals, here they're shown as a pi system, but the p orbitals are perpendicular. So they're perpendicular to the carbon or the plane of the molecule, and they overlap in a ring on the top and on the bottom. Now remember that pi system is both the top and the bottom. They're not separate. They're all one system, just like a normal pi bond. So that would be our structure of benzene. Now I've got another one here. This one's kind of cute. I made this one as a Christmas ornament that I gave out to my friends a few years ago. My friends have come to expect that they get kind of nerdy gifts. So this is one that I again designed it, 3D printed it, and then gave it out to my friends. And I made one side of it red and the other green, so it would look like a pretty Christmas ornament. And you can see right there that you just put a hook on there and it hangs on the tree. Kind of cool. All right, so let's go back. Next, we want to look at the nomenclature for these aromatic hydrocarbons, these substituted benzenes. So to name a benzene ring with one substituent, you simply name the substituent and then add the word benzene to the end. It's pretty easy. And because wherever that substituent is carbon 1, we don't have to put a number on monosubstituted benzene rings. So this is simply ethylbenzene, terbutylbenzene, and chlorobenzene. There are a few names that we use that have common names that are associated with them, and in fact they're so common that they've become part of the IUPAC nomenclature system. And so these are monosubstituted benzenes that have their own special name. And so this one is called toluene methylbenzene. It's toluene. Toluene is used as a solvent, an alternative to using benzene. It's got some of the good properties that benzene has, but it's not nearly as carcinogenic, so it's desirable that way. Hydroxybenzene, we refer to that as phenol. Phenol, you may have heard of that in terms like for medical use. It's called carbolic acid, and it is a very effective antiseptic. It's also a little bit poisonous, but you know, hey, most of these are poisonous. And then next we've got aniline. Aniline is aminobenzene, and that is just the common name for that compound is aniline. And as I mentioned, these have become such common names that they have been incorporated into the IUPAC system. When we have disubstituted benzene rings, there are different ways that the two groups can be attached to the benzene ring, and so we give them designations depending on how far apart they are. So if we have 1,2 substitution, we refer to that as the ortho isomer. If we have 1,3, we refer to that as meta, which just means in between. And if we have 1,4 substitution, we refer to that as para, which means opposite. So ortho is adjacent, meta is in between, and para is opposite. So 1,2, 1,3, and 1,4. That means that you can name this in two different ways. You can refer to this as ortho dibromobenzene, or you can refer to it as 1,2 dibromobenzene, 1,2 dibromobenzene. Both of these are correct. So ortho dibromobenzene or 1,2 dibromobenzene, both of those are satisfactory. You need to know, of course you know the numbers already, but you need to know what the ortho, meta, and para mean if you see it. This one we would call meta dibromobenzene or 1,3 dibromobenzene. And this one would be para dibromobenzene or 1,4 dibromobenzene. If you have two different groups on the benzene ring, then we need to know what order to put them in. If it's two different groups and it's not part of a common name, then we are going to alphabetize the substituents, where the first one alphabetically gets the 1 position, and the second one gets whatever the other position is. For example, here we've got a bromo and a chloro. Since B comes before C, this would be ortho, and these are ortho to each other. This would be ortho bromochlorobenzene. It would also be accurate to call this 1-bromo 2-chlorobenzene. That would be an accurate description of that molecule. On this one, we've got nitro and fluoro. Fluoro comes first alphabetically before nitro, and so as a consequence, we would call this meta-fluoronitrobenzene. Or we could call this 1-fluoro-3-nitrobenzene. That would also be a correct name. I will be doing it both ways if we have a disubstituted benzene ring. Another thing that we will see is if one of the substituents makes up one of our common names, toluene, phenol, or aniline. All right, I had to think what the other one was there. So toluene, phenol, or aniline. Then we're going to name the molecule. The parent name is going to be the name of whatever that common name is. So like this would be toluene. And whatever the position of that is, that's the 1 position. So the toluene has a substituent that's methyl. We're going to call that the 1 position. And so this bromo is in the 4 position or the para position. So we could call this para-bromotoluene, or we could call it 4-bromotoluene. That would be sufficient. On this one, we have ortho-nitrophenol, or again, we could call this 2-nitrophenol. Well, what if we have 3 or more substituents? In that case, we're going to not use the ortho, para, and meta prefixes. We only do that for disubstituted. For trisubstituted, we're going to stick with the numbering. So we want to number to give our lowest possible numbers around the ring. And so in the case of this, we've got 3 substituents. Since we have 2 that are adjacent, the 2 that are adjacent are going to be 1 and 2. And since we have 1 that's here opposite of this ethyl, we have this chloro, then we're going to number clockwise to give that one the lowest possible number. If we called this one 1 and that one 2, this would be 5. So we want to number it to give this also the lowest possible number. So in this case, we would number it that way, but then the naming is still going to be alphabetical. So we have an ethyl group, a chloro group, and a propyl group. Well, chloro comes first alphabetically, so it would be 4 chloro, 1 ethyl, 2 propyl benzene. So we alphabetize the substituent names. If we have a common root, so toluene, phenol, or aniline, and in this case we have the aniline, then we're going to name the molecule as a derivative of that monosubstituted benzene. So this would be aniline, and we would have chloros at the 2 and the 5 position. So this would be 2,5-dichloroaniline. And so this is a little bit different than this. If we were going to number this the same way, we would call this 2-amino 1,4-dichlorobenzene. But here, since we're going to name it after aniline, we're going to call it 2,5-dichloroaniline. All right. In the case that we have a benzene ring as a substituent, well, if it's a substituent that is directly attached, we're going to call that a phenyl group. And so we can represent that shorthand. We can just put pH, uppercase P, lowercase h, for the phenyl group. We can also write it as C6H5- as a substituent if we don't want to draw out the entire benzene ring. Sometimes it's not convenient to draw out that entire benzene ring. So either the phenyl or the C6H5- would be sufficient. All right. That pH, we can use that in other contexts. So anytime we have a benzene ring and we're trying to do shorthand, we can put the pH in place of the phenyl group, which is the C6H5, and then whatever's attached. So pH and then uppercase H, we can represent that as benzene. And if we want to represent phenol, we could do pH OH, and that is another way that we represent. It's a shorthand way of representing phenol. All right, one other thing, and that's benzyl and aryl groups. The benzyl group is a little bit different than a phenyl group. A benzyl group has a phenyl group in it, but it also has a CH2, and then that is attached to whatever your substituent is. So it's C6H5CH2. The reason that we separate out benzyl groups is that benzyl carbons have special reactivity. We're going to see all kinds of examples where we can do reactions at that benzyl carbon that we wouldn't be able to do on a normal sp3 hybridized carbon. So you want to be able to differentiate between the benzyl and the phenyl. And in case you're curious, if you want to abbreviate the benzyl, so we have pH for phenyl, you can abbreviate benzyl by putting uppercase B, lowercase n. I say that because I don't want you to use BZ. We use BZ for benzoyl. We'll get to that one later, but that one involves a carbonyl. And then, generally speaking, if we are referring to substituents that have aromatic rings in them, we're going to refer those as aryl groups. So aryl hydrocarbons or aryl components are going to have a benzene ring in it. So this toluene or toluene is an aryl group. So there we go. So let's look at number 23, and we're going to give IUPAC names for several compounds. So I'm going to switch over here. All right, I'm going to lower my camera just a smidge here. All right, for monosubstituted, very easy. We just name whatever the substituent is and benzene. And because that substituent, it's a butyl, but it's attached to the second carbon on the butyl, we call this sec-butyl. So this we refer to as sec-butyl benzene. So sec-butylbenzene. All right. Here we've got two substituents. We've got an ethyl and a chloro. We need to indicate which one is which. We're going to do the chloro, because it's disubstituted, we're going to do the chloro first. And so there's two ways that we can refer to this. We could refer to this as meta chloro ethyl benzene, no spaces in there. Or we can refer to this as 1 chloro 3 ethyl benzene. And that would be correct as well. So this would be the 1 position, and the ethyl would be the 3 position. All right, on this one, we're going to name this with the root phenol. All right, so we'll call that one a phenol. And we have 2 nitros that are attached to the phenol. Since we're naming it a phenol, that's going to be carbon 1, and the next one we want to have the lowest possible number, so that's 2. And then as we number around the ring, 3, 4, 5, 6, I can label it, but there's nothing on it. So we have 2 nitros that are attached to phenol. So this would be 2, 5 dinitrophenol. So 2,5-dinitrophenol. And again, that phenol is its own unique functional group. In a similar fashion here, we're going to name this after the common root aniline. So that is aniline, and we have bromo at the 2 and 3 position. So 1, 2, 3. So this, we're going to name it as 2,3-dibromoaniline. And that would be the name of that one. All right, and then finally here, this one also is an aniline, so this is our base group. Since it's disubstituted, there's 2 ways to name this, but because we're going to name it after that root, we're going to call that one 1 and that one 2. So this could be either be ortho chloroaniline, or if we wanted to use the number, we could just call it 2 chloro. I left the A off there. Aniline. So 2-chloroaniline. And then finally, here we've got an example where we have a phenyl as a substituent. So our parent is going to be cyclohexane. We have a bromo and a phenyl. Bromo is going to come first alphabetically, so we'll call this 1 and 2. All right, and if we look at the stereochemistry, they are cis to each other. So we're going to refer to this as cis 1 bromo 2 phenyl cyclohexane. All right, and that would be the best name for that one. We're going to talk briefly about spectroscopic properties. We've talked about spectroscopic properties before when we did the chapter on mass spec. We talked about that in spectroscopy A. Spectroscopy B, we talked about IR, and in spectroscopy C, we talked about NMR. Just as a reminder, these are the things that are relevant for aromatic compounds. So remember where the carbon-hydrogen stretching is for carbon sp2. It comes out between 3150 and 3000 reciprocal centimeters. So that one is one that you know. And then we have 2 absorptions that are associated with benzene rings, with phenyl rings, aryl rings, arene, however you want to call it. And those are two peaks that are at 16 and 1500 reciprocal centimeters. Remember that these numbers can be within about 15 or 20 of that number and still be valid. It just depends on what's attached to it that will affect where they are. For proton NMR are aryl hydrogens. The hydrogens that are directly connected to the benzene ring are going to have absorptions out at 6.5 to 8. They're highly deshielded protons. And that's because of the aromatic ring. So 6.5 to 8 parts per million. And for the benzyl, this is kind of like the allylic ones, where the hydrogen's going to show up in the 1.5 to 2.5 part per million range, somewhat deshielded compared to other carbon sp3 hybridized carbons with a hydrogen on them. So benzylic 1.5 to 2.5. You'll want to know that. For the carbon NMR, we're going to find that they all fall in a range from 120 to 150 parts per million. Remember, for carbon NMR, our total range is from 0 out to about 220, and this falls in that relatively narrow range, 120 to 150. What's attached to it will affect these numbers. If you have something very electron withdrawing, it will pull this. It will pull it downfield. And if you have something that's electron donating, it will pull it upfield. All right. Now, there is something that's very interesting that you can determine when you have disubstituted, when you have two of the same substituent on a benzene ring with carbon NMR. You can determine what the substitution pattern is. So if you have dibromobenzene, ortho, meta, and para, you're going to get a different number of carbons depending on what the substitution pattern is. So the number of lines, remember they show up essentially as singlets, as lines in the carbon NMR spectrum. So the number of lines will be when you have two identical groups. It all depends on whether it's ortho, meta, or para. So if you've got the ortho dibromobenzene, there are three different types of carbons. So the two carbons that have the bromine are identical. These two carbons that are adjacent are also identical. And these two carbons are identical. Remember, if you can put a plane of symmetry through it, like you do with this one, then that means the things that are opposite each other are identical. With the meta-dibromobenzene, we'll find that, again, the two carbons bearing the bromines are identical. These two carbons, the two green ones here, are identical. But then this carbon that's between the two bromines is unique. And this carbon out here that is furthest away from the two bromines is also unique. So there we get 4 carbon NMR signals. With the para-dibromobenzene, we have 2 planes of symmetry. We have one that goes right down the middle this way and one that goes this way. So that means that these two are identical, these two are identical, but then these two are also identical to these two. So we only have 2 types of carbons in the signal. All right. At some point, you can do this now and pause the video, or you can think about this a little bit later. But at some point, I want you to think about what happens if I have 2 different substituents. How many peaks would I get for each of these? And you might be surprised at the answer. So, all right. But for now, we're going to go over to number 6 and number 52 on the in-class assignment. So on number 6, it says, what is the structure of a compound, molecular formula C10H14O2? Whenever you're given a compound like that, the very first thing I recommend doing is to calculate the degree of unsaturation. So the degree of unsaturation is going to be the maximum number of hydrogens with 10. 10 times 2 is 20, plus 2 is 22. We're going to subtract the actual number of hydrogens, which in this case is 14, and then we'll divide by 2. And when we divide by 2, that'll be 8 divided by 2. That gives us 4. So there are 4 degrees of unsaturation. Because this is a chapter on aromatic rings, that's not very surprising. That means that we have a benzene ring. Benzene ring in and of itself has 4 degrees of unsaturation. That would account for it. That means we also have no additional unsaturation, so we have no additional double bonds. All right, it shows a strong IR absorption 3150 to 2850, and so that covers both of our carbon hydrogen. So the 3150 to 3000 reciprocal centimeters, that's what corresponds to the carbon sp2 hydrogen stretch. And then the 3000 down to 2850 reciprocal centimeters, that's the carbon sp3 hydrogen. So when you see it stretch across both of those ranges, that tells us we have both types of carbon hydrogen stretching, both sp2 and sp3. That gives us structural information. Now let's look at the rest. All right, and gives the following proton NMR absorptions. 1.4, we've got a triplet, and it's 6 hydrogens. 4.0, we've got a quartet, and it's 4 hydrogens. Well, if we look at those, whenever we have that triplet quartet pattern, and we'll look over here, we've got a singlet that's 4 hydrogens, and it's at 6.8. We'll talk about that one in a minute, but for this, when we have that triplet quartet pattern, that is an ethyl pattern, and it matches, the numbers match here. For the triplet, we've got 6 hydrogens that are the triplet, and we've got 4 hydrogens that are the quartet. That's a 3-to-2 ratio, as we would see with an ethyl group. All right, so we've got the CH3, CH2, that's a 2 there, not a 3, and it's attached to something. And this corresponds, all right, so this corresponds to the triplet, the 6 hydrogens. There's 2 of the ethyls that are identical. And then the quartet is going to correspond to this. Because that quartet, the 4 hydrogens, is at 4.0, that tells us that those hydrogens must be adjacent to something that's very electronegative. And given that we have oxygen in the compound, we probably have an oxygen directly adjacent to those 2 hydrogens. So it would appear that we've got 2 ethoxy groups that are attached to a benzene, and that these 2 ethoxy groups are identical. All right, if we look, that accounts for everything, right? We have 6 carbons in the ring, and we've got 2 of these ethoxy groups that are identical. That would give us the other carbons and the hydrogens. Since we have 2 substituents, it makes sense that we have 4 hydrogens. And so really, this gives us just with that information, it gives us 3 possibilities. And the 3 possibilities are, where we've got the benzene ring, and we could have ortho, so CH2, CH3, O, CH2, CH3. So that would be one possibility. Another would be where we have meta. All right. And so OCH2, CH3, OCH2, CH3. And then finally, our final option would be where we have para. OCH2, CH3. Now, we can determine which one of these it is by looking at this thing. This particular one, it says we have a singlet. And for it to be a singlet, that means that all 4 hydrogens need to be identical. And that is only the case in this structure where it is para. So because it's a singlet, that tells us that all 4 hydrogens on the benzene ring are identical. If we had this one, we would have a doublet of doublets. So we would have an interesting structure there. So this would be coupled to this, and that would look different. If we had this one, we would have coupling between this, and we might get a cross coupling, that weird stuff that happens in a benzene ring, but it would be a more complex pattern. With this is the only one that would give us a singlet, because all 4 hydrogens are identical. So this structure is consistent with all the information that we have there. So we're going to also look at number 52, and number 52 actually has 3 problems on it. All right. We want to propose a structure that's consistent with each of these. All right, the very first thing I'm going to do on each of these is to determine the degree of unsaturation. On all of them, we're going to find the degree of unsaturation is 4, but we'll go ahead and calculate it. So our degree of unsaturation is equal to, so 10 times 2 is 20, plus 2 is 22. We're going to subtract 14 and divide by 2. And that gives us 4 degrees of unsaturation. Again, that's typical when we have a benzene ring, because benzene rings, the ring counts for 1 and the 3 double bonds counts for the other 3. That also means we don't have any additional unsaturations. All right, so we have carbon sp2 hydrogen stretching. That is the 3150 to 3000 reciprocal centimeters. And we've got carbon sp3 hydrogen stretching, and that's the one that's from 3000 to 2850 reciprocal centimeters. All right, the 1600 and the 1500, that is typical that we have a benzene ring. Not surprising, since this is a whole chapter about benzene rings. Now we need to deal with the substituents. We have 4 carbons. All right, we've got 4 carbons that are substituents. So we need to look at these absorbances in the NMR. First of all, let's notice that out here in the aryl hydrogen range, we only have 4 hydrogens, and it is a multiplet. With 4 hydrogens, we will find that means that we have 2 substituents. We've got 2 different substituents here. When we look over here, we've got a singlet that's 3 hydrogens. The singlet that's 3 hydrogens, all right, so it's at about 2.4, we'll call it, parts per million. So delta is 2.4 parts per million. All right, and it is a singlet, and it integrates for 3 hydrogens. That's almost certainly a methyl group. All right, and we don't have any oxygens on here, so it looks like that methyl group is directly attached to the benzene ring. If you go back and look at the absorbances that we have, or the proton NMR absorbance for a benzyl hydrogen, that fits. With that at about 2.4, that's in the 1.5 to 2.5 range, that fits. So it looks like we have a methyl. The other substituent has 1 hydrogen and 6 hydrogens, so that looks like a propyl group of some sort. And if we look carefully, we've got it's hard to see, but this is a septet. It looks like a quintet, because it looks like there's 5, but there's actually one that's kind of buried on the sides. It's a multiplet, and it's coupled to this one, which is a doublet. So we've got 1 hydrogen that is a septet and 6 hydrogens that's a doublet. That is a pattern that we see with isopropyl. So our absorbance, that is the looks like about 1.3 parts per million. All right, it's a doublet, and it accounts for 6 hydrogens. All right, and so those are 2 CH3s, and then here we've got, again, at 3. Looks about 3.1 or 3.2. We're just going to call it 3.2 parts per million. We've got a septet, and it accounts for 1 hydrogen. Again, these together is an isopropyl group. So we've got 2 possibilities here. Technically, we have 3, but 1 we can kind of rule out. So we could have the methyl there and an isopropyl there. All right, and that would be the ortho. Or we could have a methyl there and an isopropyl there. The reason I didn't draw the para, if we had the para substituent, these couplings would be a doublet of doublets. When we have 2 different substituents on a benzene ring and they are para to each other, we get a doublet of doublets. It looks a little bit more regular. And in this case, it's going to be one of these 2. With the information that's supplied, I don't know that we could figure that out. We would have to do some additional experiments to figure that out. But if we can narrow it down to 2, that's usually a pretty good job. All right, so one of those is going to be our structure. So now let's look at this one. Our degree of unsaturation, so 9 times 2 is 18, plus 2 is 20. So 20 minus 12 over 2, again, gives us 4 degrees of unsaturation. With 4 degrees of unsaturation, then that tells us that we have a benzene ring and no other double bonds. So no other unsaturations. All right. I'm going to pull this down a little bit. Okay. We've got a carbon NMR signal at 21, 127, and 138. That tells us that we've got a signal, a carbon that is an sp3 hybridized carbon, but there's only one type of that, and that we've got 2 aromatic carbons. All right, so there's only 2 peaks, 2 different types of peaks in our aromatic ring. If we look where the aromatic ring is, we have a singlet, and it's 3 hydrogens. So we have a tri-substituted benzene ring, and all 3 hydrogens on the benzene ring are identical. In addition to that, we've got 9 hydrogens in this singlet that's at about 2 point something, and that tells us that we've got 9 hydrogens that are all identical. They're all identical. All right, with the 9 hydrogens, so 6 of the carbons are going to be in the ring. With the 9 hydrogens, that tells us that we probably have 3 methyl groups on a benzene ring. And if we look at the possibilities, right, we start to weed out some things pretty quickly. So CH3, CH3, CH3. Well, this can't be it because these methyls are not identical. This one's identical to that, but these hydrogens are not identical to this, so we wouldn't get a singlet. We'd get 2 singlets there. So this can't be it. All right, if we just start going around and looking at all the possibilities, all right, 1, 2, 4. All right, again, CH3s for all of those. Well, that also isn't going to work. And the reason that that isn't going to work is because all 3 of those methyls are different. We have these 2 that are adjacent to each other. This one that's para to that one. It's ortho to, or meta to this one. This one's not going to work because that would give us 3 different methyl signals. In addition, these would not be singlets as well. And then finally, we can look at another possibility. If we start going around, we'll see that there's a limited number of possibilities. The only other one is going to be this. All right, here the 9 hydrogens that are in the methyls are going to be identical, and the 3 hydrogens that are on the benzene ring are going to be identical, and we only have 3 different types of carbons. Since these 3 carbons are identical, these 3 carbons are identical, and these 3 carbons are identical, that would account for the 3 different types of carbons. And so this is our structure. So that is our best structure for that data. All right. And then next, we've got C8H10. Again, we'll do the degree of unsaturation. When we calculate that degree of unsaturation, 8 times 2 is 16, plus 2 is 18. 18 minus the actual 10 hydrogens divided by 2, that gives us 4 degrees of unsaturation. So we're not surprised by this. We've seen this a number of times. So we have a benzene ring. If we look here, we've got the carbon sp2 hydrogen and the carbon sp3 hydrogen. All right, so because we have it on both sides of 3,000, that's why we have both of those. And I'm just going to put that together. So 3108 to the 2875. And because it goes on both sides of 3,000, we have both types of hydrogens. If we look, it's monosubstituted because we've got 5. And here we have a benzene ring. So this is benzene. All right, so we've got a benzene ring in there, and that's the 1606, 1496 reciprocal centimeters. All right, so we have a benzene, and then when we look at this, we have a monosubstituted benzene ring because there are 5 hydrogens on the benzene ring. That means only 1 carbon has a substituent on it. All right, so 6 of the carbons are in the benzene ring. We have 2 that are not. If we look over here, we've got a quartet and a triplet because these must be coupled to each other. And when we have a quartet and a triplet, that is a typical pattern of an ethyl. All right, where this is the CH2 and this is the CH3. And this CH3 is adjacent to that CH2. That's why this one is a triplet. This CH2 is adjacent to that CH3. That's why that one is a quartet. So that is a typical ethyl pattern, CH2, CH3. Since we don't have any other atoms, and we've accounted for C6H5 and then the other 5 hydrogens and other 2 carbons here, there's only one structure this could be. And that one structure is ethyl benzene. All right. And so this would account for all of that data. And it's the only one I can think of that works for that one. So, all right. Well, I'm going to stop this video here because we're already at almost 58 minutes. So I'm going to stop that video. And in our next video, we're going to look at some interesting aromatic compounds.